What is a force? A force is a push or a pull that affects an object. To describe a force, you must know two things. You need to know the size of the force and the direction of a force. Forces could be opposite of each other, or they could be pulling or pushing in the same direction. We have balance forces. In balance forces, the sizes are the same, but they're in opposite direction. When you have balance forces, there is no change in motion. Motion stays the same, so something that's going 50 miles per hour will continue to go 50 miles per hour when there's balance forces. If the forces are balanced, it could also be staying still. Nothing will make it move because the forces on it are balanced. So it doesn't change the motion. You're either going or you're not going. Balance forces. However, when the forces are unbalanced, the sizes are not the same. They're in the opposite direction. This one's smaller than that one. This is an unbalanced force, and it could change motion. If we're changing motion of something, we're changing the speed. You're either going faster, you're going slower, or you stop. So unbalanced forces change the motion. It changes movement. There are different types of forces. You have your non-contact forces, like electrical force, magnetic force, nuclear force, and gravitational force. Very often, scientists like to group together electrical and magnetic forces together because they have similar properties and characteristics. Nuclear force is your strongest force. Electrical force is the force we'll discuss first. This force is caused by an attraction or repulsion between positive and negative charges. This is caused by a transfer of electrons. The only thing that can move on the atom are the electrons. Protons can't move. They're in the nucleus. So the charge is based on either removing or gaining electrons. Examples of this could be like glue. Metals are great elements on the periodic table. They tend to like to gain electrons. I'm sorry, I'm lying to you. They like to lose electrons. Metals like to lose electrons. They give them away. But they're good conductors of electricity. They like electrons to flow right through them. Magnetism. This little picture that I drew is supposed to be the core, but my smartboard's a little bit off, of the Earth and the magnetic field. So our Earth is like a big magnet. However, this would not be representing the Earth because something's weird. Our magnetic field is really opposite. 780,000 years ago, the poles flipped. How long is it going to take for them to flip back? It usually flips every 450,000 years, so we're due. We're overdue. Don't worry, though. Scientists believe that they're going to be some warning when the pole's going to flip back again. And in Europe, they are really testing magnetic field and the strength of it so they can recognize when the flip will happen again. And we'll be able to save all those animals and our satellites and our GPSs, etc. Okay, a magnetic force is the attraction of a magnet towards something metallic, usually. Iron, nickel, some of your alloys like steel, cobalt, these are naturally magnetic. And they can cause forces, objects to repel or attract. So if you have a negative, a north and a north, you're going to make that repel. A south and a south will make it repel, but a north and a south will attract. Gravitational force is a force that doesn't hold anything. It attracts things toward other objects. Gravity makes everything fall down. So gravity has two factors that affect it. Mass and distance. Weight is the measure of gravitational pull on an object. So your weight changes when you go onto the moon. Who wants to go to the moon? You're going to be less weight when you go to the moon because you will have a smaller gravitational attraction to the moon. The moon weighs less. The mass of the moon is less than the mass of the Earth. So this ugly mouse, why it's on this page, I don't know, but it has less force because it has less weight. And this big elephant has more force because it has more mass, therefore it has more weight. Isaac Newton, though, he was a brilliant man. He uncovered the gravitational force. And today we use a spring scale to measure the force of gravity. We also use the Newton, which is his name, to describe the unit of force. And if you want to know a frame of reference, it's about 1/4 of a pound. So, Sir Isaac Newton, thank you very much. Examples of spring scale is your bathroom scale. You could use the scale in the supermarket to determine how many apples you have, how many pounds of apples you have. Pounds is the English version, and newtons would be the weight of something in the metric system. All right, so there is a universal law of gravitation. That means this has been proven. The amount of gravitational attraction depends on two things: the distance between the two objects and the mass. Larger the mass, the greater the gravity. If you take the distance and you make that larger, gravity is going to be a lot less because distance is also affecting gravity. So make something close and it's going to have a greater gravitational attraction. Nuclear force is my favorite force. This is the strongest force in the universe. This is the force that keeps the nucleus of atoms together. It's very powerful. This is the reason why we're alive, because the sun gives us energy by fusing two hydrogens together. The nucleus of hydrogen come together and make helium. So every single second of the day, we are getting light because of nuclear fusion, because the nucleus of hydrogen in the sun is being fused together to make helium. So it's giving us every single electromagnetic spectrum energy. It's giving us radio, it's giving us microwaves, it's giving us infrared radiation, it's giving us all of that radiation. Some of it gets absorbed by atmosphere and some of it can transmit through. Okay, so on this date, we discussed why do meteors burn when they pass through the Earth's atmosphere. Why does that happen? It happens because of friction. Friction occurs when two objects rub against each other. They produce heat. But it's necessary in or on the Earth because friction is a force that opposes motion of an object. If an object is going through outer space, there is no friction. But once it starts to hit the Earth's atmosphere, it's going to rub against air. If it rubs against air at a really great velocity, speed, it's going to accelerate because of gravity. It's going to burn up. So the air is going to touch that and produce heat. The more surface area contact, the more friction. So friction can be static friction when an object is next to another object at rest. Static just means to not move. So static friction is things that aren't moving. Sliding friction is when the friction occurs because something's sliding over another object. You can increase sliding friction by making something rough. And you can decrease sliding friction by making something smooth. So don't think about this. Putting pledge on your wood floors will make them slide. People will get hurt. They'll fall down the stairs like my sister-in-law did. Rolling friction occurs when wheels make contact with the ground it's on. There's less contact with the surface, so therefore, there's less friction. How can you reduce friction? Well, you can make it smooth, so you lubricate it. This is the reason why we put oil in our cars, because the parts would rub against each other. But when you put the oil on it, it makes it slippery, so that it will make your engine last longer. If you didn't put it on, you're going to seize your engine, and it's going to produce too much heat, and it's not going to be good for the lifetime of your engine. In fact, if there's no oil in your car, you're going to break that car down and it won't work again. Efficiency and conservation of energy relies on the decrease of friction. So the best machines have the least parts that rub against each other. Is there a machine out there that doesn't produce friction? Can you think of something? Maybe if it has something of force of magnetism. But every machine that I can think of has something rubbing against each other. So there's always heat produced. What if we can take that heat and channel it into something else? That would be amazing. We would save a lot of money. Magnetism. This is the force of attraction or repulsion between certain materials and a magnet. So the magnets have two poles, a north and a south pole. The north and the south pole is where the greatest magnetism is. So unlike poles will attract each other. So if you look at the lines of magnetism, you can see they're connected. This is showing you that they're attracted. These lines, look at the arrows, they're going out, showing you this little star in the middle. There's no force here that's attracting. It's only repelling. It's pushing past each other. So two like poles will push apart, and two poles that are opposite will push together. This is how your trains work when they're maglev trains. They actually push apart and it'll make the car go. So there's nothing actually touching it. So that there's less friction and it makes these trains last longer. When the parts are touching, it's going to slow it down, south and north, so they will be attracted to each other, and that's how the brakes work on the train. All right, your domains. What that means is these are the little groups of atoms that are all lined up in one direction. They're called magnetic domains. An object cannot be magnetic unless all the domains are in the same direction. So naturally, number 26, 27, and 28 on the periodic table, iron, cobalt, and nickel are all magnetic because their magnetic domains are lining up in the same direction. If you heat or drop a magnet, you're going to demagnetize it because you're going to make these domains go in all crazy directions. When you heat something up, it makes it move faster. Well, they're not going to be organized anymore. They're going to go crazy. So demagnetizing a magnet can occur if you heat it up or drop it. But if you drop a permanent magnet, that's not going to make it lose its magnetism. So we're looking at 3 pieces of metal. The first one is unmagnetized iron. And you know it's not magnetized. Look at the domains. They're all cockamamie. They're not going in the same direction. They're all crazy. This one is slightly magnetized because there's some order that kind of pointing in the same direction. And this one's strongly magnetized because they're pointing in the same direction. Break a magnet? Don't worry. Now you have 2 magnets. You have created a new pole, the south and the north. All right, magnetic field is the region or the force around the object that's magnetic. Closer to the poles, stronger the magnetic fields. We did this in class. The magnetic fields are stronger here, and you can see the iron is stronger. If you want to change or lose magnetism, heat it or drop it. This is redundant. If a magnet breaks, you now have 2 magnets. All right, induce magnetism. When you do something, you're making it happen. So you're making a temporary magnet. We did this in class. You rub the magnet along the iron nail and you will induce magnetism. You might not be able to pick up this many paper clips, but I think some of us were able to pick up a little bit more than others, and I think some people cheated and got like 6 or 7 when they really didn't. They put the magnet in there and they hid it in their sleeve so you didn't know. Oh, that was me? Comparing magnetism. The Earth acts like a magnet. The magnetism of the poles is caused by the movement of metals in the Earth's core. So inside the Earth is a solid ball of iron and nickel, and it's constantly spinning. When it spins, it releases electrons, and these ions are coming out at the poles. Right now, the North and the South Pole have been reversed. So when is it going to reverse back? I don't know. Geographic North and South Pole are not where the magnetic North and South Pole are. They're off by 23.5 degrees. So the true north should be here. The magnetic north is not there. It's really in the opposite direction. Geographic north, which is actually our magnetic south. So I don't know why this says north. It really should say magnetic south. The Earth's magnetic poles are not in the right spots. All right, so north and south are really opposite. This is really south and that's really north. The electromagnet. You can make magnets from electricity. All you need to do is run an electric current around the nail, wrap the coil around it, you make an electric magnet. We're going to be making this sometime in the future. The stronger the electric current, the more coils, the stronger the magnet. You actually saw this principle in the electromagnet lab that we did in the computer lab. All right, what use electromagnets? Some trains do, lots of machines. In fact, almost all of our energy that we get today comes from electromagnetism. We burn coal in, what is that called? PSEG. That's the name of our new electric company, charging us too much money. We burn coal there and we spin a generator by heating up water. Well, we could do that in so many better ways. Why are we burning fossil fuels? Why can't PSEG just put up like thousands of solar panels and charge us less money? I don't know. I think us people act too much like sheep and we should be stronger and fight this monopoly. All right, energy caused by moving electrons is electricity. Electrons are negatively charged particles. Protons are positively charged and neutrons are neutral. The only part of the atom that can freely move are the electrons. So where does the electricity come from? The electrons. If something has a positive charge, it's because the electrons have gone. The law of electrical attraction. Matter with the same charge repel each other. Matter with different charges attract. Positive, positive, repel, positive, negative, attracts. Very similar to the poles. Static electricity is the buildup of electric charge. They're not going anywhere. But the beauty of static electricity is you can transfer the electrons to somebody else. So you rub your feet against the carpet and you build up static electricity. You build up all the electricity and you touch somebody, zap, you get them. They become electrically charged. It's temporary though, it doesn't last too long. It happens to me all the time in the winter. I get shocked when I am driving and then I get out of the car and I touch the metal and it gives me a shock all the time. And crazy things have happened with electrical static electricity. Some people, when they're pumping their gas, go on fire. Is that not? That's crazy. Because the static electricity in their car transfers when they take the pump. That's so scary. It's very, very rare, but that's crazy. That can really happen. So it's a buildup of electrical charge on an object. I told you nylon carpets were a mistake. Get it? Their hair sticking up, too much electrons. All right. Electrical currents. An electrical current is a flow of an electron through a circuit. Insulators do not allow things to flow. That's why our wires are covered with rubber, because if they weren't, we'd all be electrocuted all the time. Conductors allow them to flow easily. Best conductors are copper. A long time ago, houses were wired with aluminum wiring. It's not too smart. It's dangerous. So if any houses right now have aluminum wire, they're not up to code. So they have to get rewired if you want to sell that house and become copper. So really old houses might have that. So if you looked inside a wire, you might see there's multiple wires that are going to be separated by those plastic. Our metals are good conductors of electricity. So the battery will transfer the electrons through and light up the light bulb. The law of conservation energy states that energy cannot be created nor destroyed, it only changes form. I could sing the song, but I feel like this video is way too long, so I'm done. How do we get electrical energy? See this spinning turbine? How does it give us electrical energy? There has to be what inside? Magnets. Those magnets will help us collect the electrons. How do we get electrons? Hey, from solar panels. They collect the electrons. There's silicone. Silicone is a good semiconductor. It's a metalloid. And that allows us to collect the electrons and we store them. So, do we need to burn fossil fuels? No, we don't. We need more of these things. There's only like 3% of wind energy that's collecting the electrons for us in the world. We need more. So all you lobbyists that are saying this is not aesthetically beautiful, be quiet. It's beautiful because it's going to make us breathe better. Maybe there'll be less asthma in the world. All right, electrical circuits, the path that the electron current follows. So you have pieces that electrical engineers tend to refer to as our source. They don't call it a battery or an outlet. They call it a source. So where are you getting your energy from? Your load, which would be your appliance or your device. In our class, our loads are going to be our light bulbs. Resistant, that's just something that's going to slow down the electrical current, but we need a resistance. We need the wire. And our switch just turns it on and off. So we have types of circuits. Your first circuit is called a series circuit. The electrons flow in only one path. If one device is turned off, if one of our loads is turned off, they're all going to turn off. So long time ago, your Christmas lights, if you ever watched Christmas Vacation, if one bulb was off, they all are off. They won't go on. So Christmas Vacation is a funny example because he puts all these lights up and one of them is off. And he's trying to figure out which one it is. This is going through the same path. So if one of them is off, you break the circuit. A parallel circuit is better. It follows through more than one path. Most of our homes and our schools are wired because if one goes off, the whole school won't have electricity. Maybe some of you kids would like that, but the teachers wouldn't. So each classroom is wired with its own separate wiring. In your house, the same thing. So when you turn on the light in the kitchen or you turn it off, all the lights aren't going to go off, but I think I need this in my house. I want one circuit for everything because my kids always leave the lights on. So if I have one circuit for everything, I can shut them all off at the same time. Good idea? I think so. And that is the end. Phew.